for Chapter 11, Properties of Solutions. Primarily today we'll be talking about vapor pressure in solutions. So we're going to go into a little more detail than we did in Dalton's law, and we're also going to be talking about boiling point elevation and freezing point depression. So if you remember from our earlier chapters when we talked about the concepts of vapor pressure, we were talking about the idea of there's this equilibrium between the solution or the solvent or whatever we're looking at, the liquid, and its liquid state and its gaseous state, and that we end up, once we have a closed system, an equilibrium occurring of the equal rates at which the solution is turning into, or the liquid is turning into a vapor and condensing back into a liquid. Obviously, pressure is the vapor pressure is going to be dependent on things like how volatile the solutes are and the solvents are, and that is dependent upon things like intermolecular forces. We'll be utilizing this concept through Raoult's law, which has the equation that we see here. And so the observed pressure on the whole system, right, of the solution is going to be the mole fraction that we talked about earlier in part 1 of the solvent, and the vapor pressure of the pure solvent. So remember that when we have a pure solvent, like for example water, and then we have a solution, for example like salt water, the NaCl that is dissolved and dispersed throughout the water is going to have an effect on that. So non-volatile solutes simply dilute the solvent. So we need to take that into account when we're talking about what kind of pressure we're going to have. So this can be represented on a line. So we would end up with a straight line, a y equals mx plus b. And so here's the breakdown of what each of these would be. Now it's important to remember the b in this case is going to be 0 because this is a line that runs straight through the origin. So here's an example of a plot of that where we have our linear line. So this is the mole fraction of solvent, 0 to 1 over the pressure of the pure solvent. And so here we can see what we would end up with as our, depending on where we are on here, we could predict what our P of our solvent would be. So we can calculate expected vapor pressure of a solution using all these different variables. So go ahead and follow through. I would encourage you to pause here, utilizing Raoult's law to solve for this. So in this case, this is Raoult's law as we would be using it, since our solvent will be our water. We need to calculate the mole fraction and determine the vapor pressure of the pure solvent. So if we know how many moles of sucrose we have, if we know how much water we have in terms of grams, we can determine the mole fraction. And then we can utilize that along with our vapor pressure of the pure water to determine the vapor pressure of the water in this solution. So as we lower the vapor pressure, we're going to be able to help count molecules. So experimentally, this is how we determine molar masses. It also helps us give some understanding about kind of the nature of how different solutes dissolve in their solvents. Now, of course, obviously we can have a non-ideal solution where both components are volatile liquids. So if we have two volatile liquids that are mixed together, then we have a solute and a solvent that are both volatile, which means they both will contribute to the vapor pressure. So in that case, we have to have a modified version of Raoult's law, which would look something like this. And basically, it's just a combination of those two different mole fractions from both the solvent and the solute, or two solutes, or anything like that. So the behavior of various types of solution, right? Again, we're going to go back to kind of our thermochemistry. We're talking about the delta H, where we're going to have a large negative delta H. That would be referring to something where we're having kind of a example like we have down here with acetone and water. When we have an endothermic solution, a delta H of solution where it's endothermic, we're going to have a situation that we have kind of down here, that we have the example of our ethanol and our hexane. Polar, nonpolar. If we have two very, very similar liquids, the delta H of the solution is going to be essentially zero because they're going to pretty much behave similarly. And so it will resemble Raoult's law very, very closely. And so an example we have for that is benzene and toluene. You don't need to know the names of these compounds, just obviously looking at the fact that they're both very, very similar in their physical shape. So here's an example where we can calculate the vapor pressure in a liquid-liquid solution. So go ahead and try this one. Remember that we're going to have to use our our kind of tweaked Raoult's law. So again, we need to go through and figure out how many moles of each of the materials we have so that we can figure out the mole fractions. Once we have the mole fractions, we can go through and solve for our total pressure, right, our expected value. And we can, again, think about it in terms of this, right? Think about the intermolecular forces that would be going on here. Acetone is going to be polar, chloroform is going to be polar, which means there will be a dipole-dipole interaction occurring here. So this all comes back to intermolecular forces, so you still need to be comfortable with those. So solution is made by mixing hexane and chloroform. What type of deviations would we expect? We would expect a positive one. I would encourage you to actually pause through each of these and answer them. Since we write an explanation with them, I won't go into too much detail. If you have a specific question with one, I would encourage you to come spend some time with me in office hours so that we can go through it in detail and make sure that you're understanding the concept that we're discussing. One of the last concepts that we're going to talk about in this video are the concepts of colligative properties. The two that are most common that we discuss will be boiling point elevation and freezing point depression. These are obviously physical properties of different materials, boiling point and freezing point. But when we have a solution, when we have a solution with, a different solvent, that solvent's boiling point and that solvent's freezing point will be affected by the solution. So boiling point elevation, it may sound silly, but basically what it's telling us is that in certain situations we will observe that a solvent's boiling point will be higher than it normally should be when it's in solution. So this, you've probably observed this in your kitchen. If you've ever boiled water, you've added salt to the water if you're making pasta. You notice that it takes longer for that water to boil than just a regular cup of water. And that's because of boiling point elevation. We now have a solution of salt water instead of water. So the boiling point of the water has been elevated. And we can use this equation here for non-volatile solutes to explain this. Graphically, this is what we're representing. If we're talking about the regular boiling point versus the solvent solution boiling point, we can see that it elevates. So here are some examples of that, right? We know water. Here's the KB of water, the freezing point of water, and the KF, right? So KB is the K for the boiling, KF is the K for the freezing. So this is a good opportunity to go ahead and try and calculate the boiling point. So as we go through this, right, we know what our delta T would be, which would be this 100 degrees Celsius is the original pure water boiling point. This is the new water boiling point, so our change was 0.34. The KB for water And then we can figure out the molarity of the solution. So from that we can take the delta T over the Kb to get moles per kilogram. And if we know that it was prepared using this is our given. So we can use our conversion to make sure that we get into moles of how much glucose we have. To do that, we end up with 0.1 moles of glucose. And if we know we had 18 grams of it, and it's 0.1 moles, we'd get 180 grams per mole. Freezing point depression is a similar thing. For those of you who have gone to areas that freeze during the winter, you may have noticed that some people put salt on the sidewalk to hinder the ability of like ice patches forming on the sidewalk. And this would be an example of freezing point depression. So the freezing point of water is 0 degrees Celsius. If we make it a solution with salt, in this case table salt, that freezing point will lower. So again, here's a kind of a representation of that freezing point depression, where now we have some solute dissolved in our water, and this is going to mean that we're going to need even lower temperatures to go from the liquid to the solid state. So here is our representation equation to represent freezing point depression. And again, just like we had a Kb, now we have a Kf, standing for freezing. We can go through the same concepts that we did with boiling point elevation, now applied to freezing point depression. This concludes our last video for part 2 of chapter 11. There will be one more video. At this point, you should have started your chemistry homework for chapter 11 as well as your reading for this section. I encourage you to come with questions for office hours so that we can make sure you're on the right page.